Okay, great, thanks. So can everyone see this writing at the back? Okay, great. So yeah, I will talk about local limits of USTs, and in particular, I will use the tools that Anita presented on Monday and Tuesday to prove a result, a general result about these local limits. And I know that we received a lot of information in the last few days, so although you've seen all the tools before, I will just first quickly recap the tools we will use so that everyone's on the same page. And so just to remind you, okay, this is deliberately faint, but a spanning tree of a graph is just a subgraph, which is a tree and which includes every vertex, like that, for example. And the uniform spanning tree is just chosen uniformly. So given a graph G, it's just chosen uniformly amongst the spanning trees of G. Okay, and so I want to talk about local limits. So here's the tools we will use. Okay, and so one is local limits. Okay, and we say that Gn converges locally in law or in distribution towards a rooted graph G when I pick a uniform point in this graph and I look at the ball of a fixed radius around this uniform point, in the limit it looks like the ball of the same radius around a point here. So I will just write that. So for all, let's say H rooted, the probability in this graph, okay, and also for all R, that the ball of radius R around a uniform point, so it's telling you about typical neighborhoods, is isomorphic to this rooted graph. It should converge to the same probability, but with this limiting graph. But now we have a fixed root. And so the idea is that this is true for any fixed R, okay? So you fix R and then you take n to infinity. So this is n to infinity. Okay, local limits. And then we talked about one particular example of local limits, and that was the local limit of the uniform spanning tree of the complete graph. And it was, so I will call it T infinity, which was exactly a +1 branching tree conditioned to survive. And we said that you can construct this tree as follows. So firstly, you have an infinite line to infinity, and then you have vertices on this line. And then to each vertex, you attach a standard +1 tree, not conditioned in any way, and independently. Okay, and you do the same all the way along the spine. And so we had a theorem as well, which also said, just to make a remark, that this tree can also be constructed by you take this law and you put a size-biased offspring distribution on the spine, and then you do the same operation with these subtrees. And so it doesn't seem like it's exactly the same here, because here I drew a first spine and then added the subtrees. But actually you can check that for the Poisson law, size biasing is exactly the same as adding 1. So it's consistent with the other definition. You can just check by hand. But so this is what we will have in mind. And we also said if T is the unconditioned version, then we said that if we want to look at the probability, if we want to look at probabilities for this tree, in particular probabilities like this, then we can relate it to probabilities for this tree. And there was a formula which said that the probability in the infinite tree, so here we have a root, let's call it a rho. The ball of radius R is isomorphic to a given tree with a root is equal to So it's almost equal to the same probability for the unconditioned one, but there's a bias. Or even we don't need that isomorphic, we can just say equal. And the bias is by the number of vertices in the final generation. Because basically, if I give you the ball of radius r, then the probability you survive afterwards is proportional to the number of chances you have to survive, which is the size of the final generation, which I think we denoted by T subscript r. Okay. So that was what I wanted to remind you about local limits. Okay, I wanted to put everything on this board, but I won't succeed, so never mind. And then I also wanted to remind you, or maybe I can erase this, about a few tools. So we saw lots of things for USTs, and one thing we saw was Kirchhoff's formula.
What is T sub r? That line?
T sub r is, I will label it, it's the number of individuals in generation r. So, okay, this only makes sense if you have a tree which has height at most r, okay? And of course, if it has height strictly less than r, it should be 0. So that's consistent because then this will be 0. But if it's a tree of height exactly r, then if you have more vertices in generation r, then you have more chances to survive. So this is why you get a bias by this factor when you consider this conditioned version. So it's the number of individuals in generation. Okay, so Kirchhoff's formula, so we want to talk about local limits of uniform spanning trees, and it tells us a way to calculate a probability that a specific edge is in the spanning tree. And we said, okay, I still think this is an amazing formula. We said it's equal to the effective resistance of that edge when you view the graph as an electrical network where each edge is like a wire with conductance 1, and this is exactly the physical quantity effective resistance. And so roughly speaking, the reason it's true is because there are many links between random walks and harmonic functions, and we saw that there's Wilson's algorithm, which means you can sample a uniform spanning tree using random walks. Equally, effective resistance is defined from a voltage, which is also a harmonic function. And because we know many uniqueness properties for harmonic functions, which means often we can equate one harmonic function coming from electrical networks and one coming from random walks, and then this is kind of how you can justify this formula. So that was Kirchhoff's formula. Another thing we will use is Foster's theorem, which, if you know Kirchhoff's formula, it's just an easy corollary, but otherwise it seems a bit mysterious, which tells us that if I sum over all edges in a graph the effective resistance of the edges, what should it be equal to? So this tells me I'm summing these probabilities. So this is just the expected number of edges in a uniform spanning tree, which is actually not random. It's always exactly the number of edges is the number of vertices minus 1. So this will be the number of vertices of G minus 1. Okay. And another corollary we noted, which is that if we take any two vertices, x and y, we have a lower bound. And okay, in the notes, it was stated when x and y are not neighbors, but actually I will use it when they are neighbors. So technically you should put a +1 compared to what we wrote in the notes or in the slides yesterday. This is a deterministic lower bound on the effective resistance. And there was one more thing I think I want to recap, which is the spatial Markov property. And I just want to use it for one edge at a time. And so it tells us how to condition on events given that an edge is present or not. So if I erase the graph now, but if I want to condition on the fact that an edge is not present in the UST, it's quite logical that what I should do is I should just remove this edge from the graph G and sample a uniform spanning tree of the remaining graph. And this is exactly true. And that's because there's a bijection between spanning trees which do not contain this edge and spanning trees of the graph with this edge missing. So that's USTG minus E. And so that means I removed the edge. And then similarly, I can condition on the other events. And this is maybe slightly less obvious, but you can also convince yourself there's a similar kind of argument. So if instead I want to consider, or I want to condition on the edge being present, it means I'm forcing like the two endpoints of this edge to be connected in the spanning tree. And so instead what makes sense is to actually contract that edge in the graph G, because I know they're connected anyway, and then sample a spanning tree of the remaining graph. So now you take UST of G in which the edge E has been contracted, and of course you have to add back the edge E, and so this is contraction. Okay, and again, there's a bijection between spanning trees of G containing this edge and spanning trees of this graph. So that's why it's true. I think that's everything I wanted to recap. Right, great. So now I can try, or I'll tell you what was the theorem I want to prove. So actually, this is a very recent result. From 2022. Okay, and it tells me some kind of universality result. So we said here that if I take the complete graph, then the local limit of the uniform spanning tree is this tree. And actually it tells me that this is much more general. So we let Gn be a sequence of connected graphs. Okay, I might not say, but all my graphs will be connected, otherwise I cannot take a spanning tree of connect. Maybe I'll divide this in the middle. Connected graphs. Gn has n vertices. And also Gn is a regular graph. So I'll call it Dn regular. But I want my Dn to converge to infinity. It can go very slowly, but it just must go to infinity. Then the same theorem is true. So then if I take the uniform spanning tree of Gn, this converges locally in law towards my, what was it, T infinity. T infinity, which is the Poisson one condition to survive. Okay, so I basically want to, it will just be a sketch, but I just want to sketch this proof using these tools. And what's really amazing is that basically this theorem tells us how we can calculate probabilities. This theorem tells us how we can calculate conditional probabilities. So we're really just going to use these theorems to calculate the probability that really this, the ball of radius r in this graph looks like a certain tree, and it will just drop out. And so to do that, you should first know what you're aiming for. What does the ball of radius r look like in this? Okay, and so my claim is that the probability that the ball of radius r in this graph, so this one has a root, I should put the root really, sorry. And also I should have put it here, okay. So around the root, the probability that is isomorphic to a given graph. So maybe we'll just have one in mind, like this. So this will be for r equals 2. Okay, and so this is I always draw the root at the bottom. This is equal to, so again, this factor TR, which is the number of individuals of generation R, or sorry, it's maybe the set of individuals, times e to the minus, and then we take the number of individuals at generation strictly less than R. G, okay, I'm trying to put less than R here, okay, divided by the stabilizer of T. And so what's the stabilizer? This is the number of root-preserving automorphisms of T. Okay, and so this is very easy to prove. And so how do we prove it? So firstly, I have a formula to relate this probability to the unconditioned probability, and I know how to deal with the unconditioned probability because I just multiply for all the individuals. So firstly, I will apply this. So it's enough to show that this is equal to the same thing, but without this factor. Okay, and so what's the point? So a Poisson tree, it's a Gaussian tree, is inherently planar, which means that for each individual, its offspring are ordered from left to right. So if I want my Poisson tree to look like this, it might look like this, so the one I drew, or it might also, I could switch these two children, and so it might also look like this, which, so it's a tree which is isomorphic to this tree, so it's still counted in this event, but it's not the same event for the Poisson tree, because we've switched the order and these are counted differently for Poisson trees. So I have to count how many ways can I draw this in the plane. So this probability, so let's do it here. Probability rho R isomorphic T0. Okay, it's going to be sum over the number of embeddings. Okay, so maybe I will call the embedded version T prime. The probability that it's really equal to that embedded version. Okay, and okay, so how many, we can count how many embeddings are, and then we can calculate this. And so the number of embeddings is equal to, okay, so what's the point? So here I said I can switch these two subtrees and I get two different embeddings. However, if I switch these two above this individual, if I switch these two subtrees, it doesn't change anything because there's some symmetry there. And so in principle, the idea is that you can switch above every vertex, you can switch the two subtrees above it or the k subtrees above it, but there might be some of these switches which don't make any difference. So what you do is you count like all the switches and then you compensate for the fact that some of these switches don't do anything. So what you get is that the number of these is going to be the product over V, which, product over all V. And so we can do this for all V which are strictly below the last level. Or even, okay, even at the above level, the last level because it's 0. So let's just say all V and C. Okay, maybe let's just do it this one. Okay. And so then we have all the permutations for all the children. And then we would get this, but then because we've overcounted, we've basically overcounted by a factor every time there's some symmetry of the tree, which is exactly counted by this factor. So we get this stabilizer of T. And then what does this one look like? Okay, so it's just a Poisson probability. So we just take, so even if I change this, it doesn't change the offspring numbers. So we just take the product over all the individuals up to generation R of the Poisson probability of having the right number of children, which is product over V. Okay, and there's nothing to say for the final generation because we don't know what comes above level R. So vertices below level R, and then what's the Poisson probability? It's e to the -1. We have a 1, but we don't see it, divided by the number of children. Oh yeah, and so by the way, sorry, this is the number of children. Factorial. It's just a Poisson probability. So what we see is that we have it doesn't depend, so we have the number of terms times this probability. And so immediately this product with the factorial will cancel. And so what we get is we get this product of V below level R e to the -1 divided by the stabilizer. But of course, this is just the number of terms in the product. And so we get what we wanted. Okay, so this is how you derive the probability for the Poisson tree. And so we will use this. The aim now is to prove, we want to prove this theorem here. We need to prove that if we consider the ball of radius R in this graph, then the probability, the corresponding probability converges to the same thing. Okay, so let me do this. So what do we know about USTs? So I said, okay, we pass between the infinite version and the finite version. And how do you pass between them? You add a factor of this TR. Okay, that's okay. And so it's enough to show that for the finite version, you have this formula without the TR. Okay, and then you put it back together, and so it's all good. Are there any other questions? Okay. And so now let's calculate the same thing for the UST. And so GM. So what do we need if we want to calculate the probability that the ball of radius R in the spanning tree is equal to something? So let's take the same example. Let's suppose that our graph is 4 regular. Okay, I need to think about all the ways I can embed this rooted tree in my graph. And then sum over all the ways, the probability that this way is exactly what I see is a ball of radius R. So for example, with the same tree, one way to embed it might be like this. It's the same tree. And so the idea is that we write the probability that the ball of radius R in the spanning tree around a uniform point that is isomorphic to a given tree. It's just the sum over all embeddings. So now the embeddings are not in the plane like before, but now they're embeddings in the graph. But okay, I will also just call it T prime. I guess we can keep the root. The probability that it's really equal to that embedding. UN equals T prime. Okay, maybe we call this A prime. Okay, so if this is my particular embedding I want to do the sum, and then I want to consider what happens for each term in the sum. So say I fix an embedding and it's like this. Okay, so what do I need for this event to happen? So firstly, I need, so what do we need or what happens? This is given the embedding. Okay, so firstly, I need my root to be this vertex here. Okay, so we need the root, let's call it 1, to be O prime. Okay, then I also need that all of these orange edges are in the uniform spanning tree. So E1 up to E4 need to be in the spanning tree. Do I need anything else? If I'm saying that the ball of radius R around a uniform point should be exactly this orange tree, do I need anything else? Exactly, so which edges should not be present? Exactly, so for example, this edge I know it could not be present because otherwise my ball of radius r, it would not look like this, but there would actually be a third one coming off. So I know it must not be present. And in the same argument goes for any edge which I could potentially attach and add to the ball of radius r, it also has to be missing from the spanning tree. Okay, and so I can label these edges. So we have, let's see, this is generation 1. Okay, so we have F1, F2, F3, F4, F5, F6. So I also need the F1 up to F6 are not in the uniform spanning tree. Okay, and then once I've done that, the final step is to the sum over embeddings. So we need to count how many embeddings, basically. Okay, so I'm basically going to estimate the probabilities of all these events and just multiply them. So maybe some of them will be conditionally on the other ones. Okay, so what do we know? So step 1, easy. So I'm picking a uniform root. So what's the probability that it's really this given vertex? Yes. Yeah. Embeddings. Okay. And so I'm going to just do all these steps by turn and estimate them. Okay. Okay, so the probability that a root is equal to my specified vertex. So I have a uniform root. There are n vertices, so it's just 1 over n. Okay. Easy. Now I want to look at all these probabilities. Okay, so what I need to do, okay, that's something I forgot to say. What I need to do is I want to figure out how to use the effective resistance to calculate it. And at the moment, we only have a lower bound on the effective resistance. However, what we want to do is come up with not just a lower bound, but really something which is a good approximation. So I'm going to write use effective resistance. Okay, and what's the thing we can do to get a good approximation? So there I have a deterministic lower bound. So what does it tell me? So an observation, which is that the effective resistance between two vertices is deterministically lower bounded by, or the graph is deterministic anyway, 1 over the degree. So in this case, it's a regular graph, so it's dn plus 1, plus also 1 over the degree. Okay, which is, okay, we won't worry so much about the plus 1, it's just roughly 2 over the degree. Okay, but Foster's theorem tells me something as well. It tells me that if I sum over all edges in Gn, the effective resistance, but then if I additionally divide by the number of edges, okay, so I know what this sum is, it's just n minus 1. How many edges are there? It's n times dn divided by 2. So I have n times dn, and I have a factor of 2. Okay, this is also asymptotic to the same thing. Okay, so this is basically telling me the average effective resistance, or if I pick a uniform edge, the expected effective resistance of that edge. And so if I know that for all edges, I have a deterministic lower bound like this, and I also know that the expectation for a uniform edge is equal to roughly the same thing, it means that actually nearly all the edges have effective resistance close to this. Because, okay, it cannot be smaller, also cannot be a lot bigger, because if it's a lot bigger, it either needs to be compensated by something a lot smaller, which is not possible, or compensated by many values, which are a little bit smaller, which is possible, but I can only run this argument for a small amount of edges. So if you want to say that formally, you can use Markov's inequality on the difference between this and this. But the conclusion is that this is actually a very good approximation of the effective resistance. And so I'm going to use that approximation in the calculations that follow. So, say for most edges x, y, the effective resistance between x and y is roughly equal to, I'm not saying precisely what I mean by roughly equal to, 1 over the degree of x plus 1 over the degree of y. And so this is the formula we will use to do all of our calculations for steps 2 and 3. Okay, so let's do it. Okay, maybe I'm just going to write this. So it was t r e to the minus t less than r divided by the stabilizer t. Okay, so now I have my edge E1, which was over there, and so I'm doing step 2. So the probability that E1 is in the UST of G, N. Okay, and maybe I'll also abbreviate D instead of Dn. Okay, so we know that this is equal to the effective resistance of the edge joining, say, x to y, and we're going to approximate it by this. And so we're regular, and so it's just 1 over dn plus 1 over dn. Or 1 over d plus 1 over d. Okay, great. This is approximate. Okay, and then I want to look for the whole sequence of edges. So what's the probability that the second edge is in the UST, given that the first edge is in the UST? Well, okay, now I've conditioned, but that's not a problem because I know how to deal with my conditioning. So what do I do to condition on this being present? I should contract this edge. Okay, and when I contract this edge, then this creates a super vertex here, and the total degree will be the original degree here plus the original degree here, maybe minus 1, but because I lost this edge, but it doesn't matter. So basically, I've macroscopically, up to a small error, I've just added the degrees of this vertex and this vertex. So it becomes 2D, so I get 1 over 2D plus 1 over d because the other endpoint is unchanged. Okay, let's do one more. Given E1 and E2. Okay, and now I should contract both of them. So I should first contract E1, so I get 2D instead of D. Then I should contract E2, so instead I get 3D. So the first one will be 3D plus 1 over D. And you can see that when I do EI to E minus 1, what we're just getting is an I which appears here from the contraction. So we're going to get 1 over I d plus 1 over d. So when I multiply this all together, so probability that all the edges are there, and so in this case there were 4 edges, but in general the number of edges will be the number of vertices in the tree minus 1. So we'll go up to E t minus 1, the probability that these are all in the UST. Okay, so I should just multiply all these probabilities up to this number. So I have product I equals 1 to t minus 1, and I have 1 over I d plus 1 over d. Okay, and so what can I do? I can factor out the d, for example. Okay, and then I have the product 1 plus 1 over I. And then, okay, I'm just doing lots of approximations. I'm going to approximate this. So for most of the terms, I is large, this is small. I'm going to approximate this by the exponential of 1 over I. Product exponential 1 over I. Okay, and then I just need to sum the harmonic series up to t minus 1, so I get log of t minus 1. So I get exponential of the log of t minus 1, which will give me something like d minus t minus 1. And so it should be t minus 1, but I will just write t because we don't worry about the plus 1, or the minus 1. Okay? So that's the first step. Let's do the second term. Okay, so now we want to look at the probability that all of these edges F are not present. Okay, so it's going to be the opposite, but we have to condition on the fact that these are already present. Okay, because in the end we will just multiply everything. So for step 3, what's the probability that F1 is not in the UST, given that E1 to ET minus 1 are in the UST? Okay, so now it's a negative event, so it should be 1 minus the effective resistance. Okay, and what's the effective resistance? So what we do now is we've contracted all of these orange edges into a big single vertex, and all of these Fs are incident to this vertex. And so what we have is we have one super vertex where the degree is equal to the number of edges the number of vertices in this tree times the original degree, roughly, up to a small error. So we have 1 over t times d plus the other vertex will, in general, it will just be a new vertex in the graph. So it's 1 over d. Okay. Now what about F2? So now we have the condition on E1. Okay. But we also have the condition on F not being in there. Okay, so now what does it mean? It means that we contract all these orange edges to a super vertex, but then we know that F1 is not present, so we delete one of its neighbors. So the degree decreases by 1. And actually in the first step, it doesn't make much difference, it's minus 1. But after a while, it will start to add up because there are lots of these Fs. So we'll keep track of the minus 1. So we get 1 minus 1 over t d minus 1 is 1 over d. Okay, and let's just do one more. Okay, F3, great. Same idea. So now we condition on all the E's. And F1 and F2 are both not in the spanning tree. Okay, and so it means we contract all the orange edges, we have our super vertex, but now we deleted 2 edges which are next to it. So we have a minus 2. And so you can see that what's happening each time is that we're reducing this by 1. So when I do the ith one, okay, I will have 1 minus 1 over t d minus I plus 1 over d. And just
you can apply this special Markov property somewhat jointly, is it, with adding and subtracting?
Yes. So okay, maybe what I should say is you can keep. Okay, then if you want to take the UST of this one, and then also delete an edge, you then remove an edge from this one, which is like removing 2 edges. And likewise, if you want to include multiple edges, you then just apply it to the new graph, and you can combine in whatever way you like. Okay, so this is a general formula. You might be slightly worried that, for example, this edge, it's not true what I said in my approximation, because actually, when I contract everything, this will be like a self-loop and it cannot exist, right? The probability is 0. So in that case, the probability is not present would just be 1. But actually, the number of edges where this occurs will just be an order 1 random variable. And this is close to 1 anyway, so we're not really losing anything in the limit if we just assume it's like this for all I. Okay, so let's assume it's like this for all I, and then let's multiply. So if you multiply everything, you get the probability that F1, and so how many of these edges are there? So in this case, there were 6, but in general, every vertex which is strictly below level R in this tree will have nearly all of its neighbors, since the degree is going to infinity and there are just these 4, or in general, a fixed number of edges in the orange tree. Basically, all of its neighbors will be contributing to these Fs, apart from a very small number. So very roughly, we have the number of vertices strictly below level R times D of these edges. So we have T strictly less than R, size of this times D. Okay, and then you have the condition on all the E's. It was T minus 1. Okay, and so we're just going to multiply these probabilities. So it's 1 minus the product. Sorry, no. It's the product of 1 minus this fraction. So 1 plus T D minus I plus 1 over D. Okay, so now these will be, so it's I from 1 or 0 to, or I think it was 1 anyway, 1 to this number. Okay, these are very big, so this is very small, so this is roughly the exponential of this, so minus. I think I forgot, sorry, I forgot something. Oh no, it's good. I forget something, okay. Well, I think it's good, okay. Okay. Okay, maybe I'll continue up there. Not a good one. Okay, and so then I have product of exponential, which is like exponential of the sum. And then, oh yeah, okay, so firstly, this part, it doesn't depend on I, so I can just take it out, and I get e to the minus 1 over d times t less than r d, and so the d's cancel, and I just get e to the minus t less than r. And then for this term, I need to do the exponential of the sum, which is like the harmonic series between TD and TD minus this t less than RD. And so the harmonic series is just going to be the difference of the logs between the upper point and the lower point. So I will get the exponential of minus, so I will get log of the upper point, which will be TD, minus log of TD minus t less than RD. Okay, and already you can notice that, so here we have everything in tree, and this is in the tree, and this is everything which is strictly less than R. So if I subtract these, then I'm just left with everything at exactly level R. And this simplifies, right, because I have log of this fraction, then I have exponential of a log. So this will be equal to e to the minus t R. So what do I have? I'm going to have, sorry, there's a bracket. So I'm going to have t. I'm going to have this divided by this, so it will be t minus this divided by this. Okay, and just know that this is the same as just everything which is at level exactly R. Oh, it's not any exponentials. T. Okay, so we did, okay, there's one more step. I will just tell you very quickly. So how do we, there were the 4 steps. We did the first 3, and the final step was to count the number of embeddings. So now we have the probability for each embedding. And the step 4 is the number of embeddings. And it's just one line. Okay, so how many ways can I embed this tree in this graph? So I have n choices for where to put the roots. And then for nearly all, then I have to ask where do I put its children. So I have roughly d choices for each. It's not exactly, it's like d minus 1 or something, but roughly d. And we will do this for every child in the tree. So it will be d. And so it will be for everyone who is a child of someone. So we don't do it for the root because we already did the root here. So it will be t minus 1. But we've possibly, again, due to symmetry, might have overcounted slightly. Because, for example, in this tree, I've embedded it maybe just exactly like that. But then if I swap how I embedded these 2 edges, it doesn't change anything for the tree. And so by exactly the same argument, we've overcounted by the stabilizer of the tree. And then, so once we've got that, we just have to multiply this all together. Because the probability we found did not depend on which embedding. So we get the probability, it's the last line, that the ball of radius r around the uniform point is isomorphic to a given rooted tree. It's going to be the number of embeddings times the 3 probabilities we just calculated. So this was one of them. This was the other one. And then the first one was for the uniform root, which was 1 over n. So we have 1 over n. Then we have this, which is d to the minus t minus 1 times the size of t. And then we have this one, which is e to the minus t less than r times t r divided by t. And lots of things should cancel. So we have an n, which cancels. We have the powers of d, which cancel. We have the t's, which cancel. And we get left with these 3 terms, which are exactly the same 3 terms that we have in red on the left. So we got the right limit, and I'll stop there. Thank you for your attention.
Quick questions, anybody? So the only place we use d and go to infinity is in these approximations, right? Is that correct? Otherwise,
okay, heuristically, the reason you need it is because, roughly speaking, if you want to look at, just take a single vertex, you want to test all of its neighbors. And so you have some probability for all the neighbors. And if the degree is very big, then these are roughly independent. So you'll have something which is close to being a binomial random variable with mean 1, and this will go to plus on 1. So if the degree is not going to infinity, you're going to feel the geometry a bit more. So once you condition on this one being present or not, you will really feel that in the limit.
Okay. Good. Okay, let's thank Kelly again. I have a few announcements before we break. First thing is rooms for people in the afternoon.